All right, so today's second main lecture, we're going to move on from the input handling to the one part of the main loop that we haven't really discussed properly yet, and that's the simulation part, the core of it. Maybe the most, is it the most important? Well, they're all important, but we're going to do this one. Right. So I have this position that I claim that computer games are a type of simulation. And, yep, we did all that. And as I mentioned as well, that you can have a simulation without it being realistic. It just means that there are some type of rule of a kind that you could express in a computer program. Whether it's realistic or not is a separate matter. For example, you could create abstract systems where gravity behaves unusually, not the way it behaves in Earth or not the way it behaves anywhere. It could be totally inconsistent with physics. You could violate conservation of momentum if you wanted, or you could have a world in which eating mushrooms turns you into a giant for 30 seconds instead of making you very sick, is what they usually do. Just as long as you've got some rules. And if you think about the real world as a kind of reference for simulations, you might notice that the real world is made up of things, and the things move about, things including your good selves, and cars and birds and bits of rubbish lying in the street, and they move around in space, occasionally bumping into one another, maybe merging or breaking apart, making noises, generating heat, and just kind of doing the things that things do. So physicists have got a description for this. A physicist would say that what's actually going on is you've got atomic or maybe subatomic level particles obeying whatever laws of physics exist at that level of scale, and they're just all obeying the laws of physics. So imagine it's like there's a bunch of little let's just pick atoms, although there are things smaller than atoms. But imagine you've got your simulation and it's full of atoms, and the atoms are running a piece of code called the laws of physics. And that tells them what they're supposed to do based on, they look at the atoms that are nearby that might be causing forces to act on them, and they just work out what they need to do. They're not really doing this, right? Atoms don't actually have brains, and they aren't like running new programs, not so far as I know. But something's happening anyway, and they're obeying the laws of physics, and they're executing it almost like a program, maybe. It turns out that actually doing it this way is very tedious. You wouldn't want to build your simulation out of atom-level entities, right? That would be difficult and it'd be very slow. Also, it'd be really paradoxical, right? If you did like an atom level simulation, imagine you had like an atom object in your program. Obviously, simulating that atom object requires the work of many transistors to simulate whatever it is it's supposed to be doing, and every one of those transistors is bigger than an atom, right? So if you made your simulation atom-based, the computer that's running your simulation would have to be physically bigger than the things that you're simulating, right? So your simulation of the world would be bigger than the world. So that's not what you want, is it? You'd have a map that was bigger than the territory. You have like a map and it's on a 100-to-1 scale. This would be the other way around. This would be a map be 100 times bigger than reality. What's the point of that? So we don't simulate things at the atomic scale because it would be stupid most of the time. And in fact, so we chunk them up. We deal with some higher level thing. We take a whole bunch of atoms that happen to be sticking together in a fairly friendly manner, and we do it at that level instead. And we tend to call those things objects. Or that's one of the things you can call them. You can call them what you like, objects, things, entities. What's important to realize is there's not some hard and fast rule as to what they ought to be. It's a decision of practicality in a lot of ways. But when you look at the real world, there are certain things that are big enough to be coherent, interesting seeming things, like this bottle of water. So that's a thing. It's different from the desk. I would want to simulate it separately from the desk. But I probably won't simulate the label as a separate object. I'll just treat the label as being part of the bottle, even though I could argue that it's not. The contents, the water inside it, actually, there's a debate there. Sometimes maybe you want the water to just be treated as it's part of the bottle. But if I were to pour it out, I'd need to now start simulating the water as a separate object. And water behaves differently from bottles because this is a solid and that's a liquid. So you make these decisions as to what your objects are going to be. And that's just part of the design process. But obviously, as experienced Java programmers, I'm sure you'll know all about objects. So this is all, not new to you. And of course, in programming, we use object to describe a collection of related data and behavior. The data is, for the kind of objects we're thinking about, data would be its position and size and stuff like that. So it's got an X, Y, Z coordinate, and a height and a width and a color or various properties. And then it's got behavior, which would be methods on the object that do things like, there's something in there that tells it, what to do if you push it. So there's a push method, and if I push it, it does that. And this is what object orientation is about. Now, sometimes when I'm doing kind of game stuff, I will refer to the objects that are part of the game world as entities, which is just a synonym, right? But I tend to use entity to mean like a physical object, something that if your simulation was real, the entity would be something you could kind of touch, which differentiates it from abstract things. A simulation might have abstract things like a collision detection system, which you can't see, or a high score table, or it might have like user interface elements, right? So the user interface elements, they'd be objects in your system, but they're not entities because they're not really part of the simulation environment. So that's just a distinction I choose to make. So one point I want to make here is that this business of simulating something by breaking it down into entities is potentially artificial. It's as I say, it's a convenience decision, and you decide at what scale to do it, at what fidelity to do it, based on just identifying chunks of the world that seem relatively coherent, and you can think about them sort of in isolation, so that you can kind of design them as a part on its own, and then at some point you plug in all the other things by having methods being called and stuff. So this is the somewhat fictional idea that the world actually is split up into separate objects, which is only true up to a point, but it's a convenient fiction that we work with, even though in reality, if you think about it at the atomic level, it's actually more complicated than that. That what things that seem to us like separate objects are actually kind of in flux with each other at the boundaries, technically. There's actually a quote about this from Richard Feynman. How many of you have heard of Richard Feynman? So he's got a little talk about this thing about things that seem like object boundaries to us or seem like category boundaries to us, but in a way those are to some extent simplifications that we've imposed on the world. I'll let him explain it because I've actually got the quote here if it plays properly.
A poet, I think it is, who once said, "The whole universe is in a..."
Hold on a sec, I'll just turn the volume up so you can hear it a bit better.
A poet, I think it is, who once said, "The whole universe is in a glass of wine." I don't know, I don't think we'll ever know in what sense he meant that. For the poets don't write to be understood. But it is true that if you look at a glass of wine closely enough, you will see the entire universe. There are the things of physics, the twisting liquid, the reflections in the glass, and our imagination adds the atoms. It evaporates, depending on the wind and weather. The glass is a distillation of the Earth's rocks, and in its composition, as we've seen, the secret of the universe's age and the evolution of the stars. What strange array of chemicals are in the wine? How did they come to be? There are the ferments, the enzymes, the substrates, and the products. And there in wine was found the great generalization. All life is fermentation. Nor can you discover the chemistry of wine without discovering, as did Pasteur, the cause of much disease. How vivid is the claret, pressing its existence into the consciousness that watches it. And if our small minds, for some convenience, divides this glass of wine, this universe, into parts, to physics, biology, geology, astronomy, psychology, and all, remember that nature doesn't know it. So we should put it all back together and not forget at last what it's for. Let it give us one final pleasure more, drink it up and forget about it all.
I think it's a good point yourself.
Part of the reason I mentioned that is that there's a longer passage about this that he has.
About the patents in the submarine.
Oh, the patents! Oh, yeah, the patents! Oh, yeah, yeah.
Bloody autoplay. I hate it when I keep switching that on. Very annoying. In fact, I should just close that. There's a thing where Feynman points out in one of his books that if you've got like a liquid in a glass, you might think, oh, the liquid's one thing and the atmosphere above it is another thing. But the reality is that there's constant evaporation and sublimation taking place between the boundary. So these things that we think of as hard boundaries, they're actually at the atomic level very turbulent. So object boundaries are not really a precise thing, which is just this whole thing I'm trying to suggest about there's a certain amount of arbitrary freedom as to where you draw the lines between your objects. So not only are the objects we were talking about turbulent collections of atoms that are actually a bit fuzzier than you might think. It's actually true of people. It turns out that my brain might be composed now of an entirely different set of atoms to the ones that it was made of when I first heard that Feynman quote, 25 years ago, because we are constantly recycling our atomic composition. As we eat, new matter is coming in and coming out. So you're actually not made of the same atoms as you were from year to year, but you're still the same person in some sense. You're still the same object. You have object identity, but your value is not the same as it used to be. Right? You're an object that's mutating over time. And yet I've still got memory of things that I was exposed to when I was made of an entirely different set of atoms, or near enough. And that's quite weird, isn't it? But that's because it's not really the atoms that are the important thing. It's the structure of them. It's the way the neurons are connected is the thing. So you can replace what the neurons are actually individually made of, as long as the connections remain the same. And that's how you can have a memory that persists, despite the fact that you're made of different hardware than you used to be. Turns out this is also true of the internet. The internet is a turbulent collection, a kind of pseudo-object, as was pointed out by a guy called Alan Kay. How many of you know about Alan Kay? I'm going to take that as nobody, right? And that's alarmingly typical, except he's like one of the key figures in all of computer science, and you should know who he is, but he's a bit unsung. Alan Kay, it turns out, is one of the people who designed the internet, although he doesn't take too much credit for that. He was one of a number of people that worked on it back in the 60s. But he invented object-oriented programming. But nobody told you who invented object orientation? No. Well, Alan Kay did, right? Not just on his own. He worked with a team of people, but he's generally considered as being like the kind of leading light, the kind of vision guy. And he coined the phrase. The phrase object orientation was Alan Kay came up with it. Although he says he regrets the phrase. He says it makes people focus on the wrong thing. He says I should maybe have called it message oriented, because the thing is, he thinks the important part is the idea of sending messages between separate parts, whereas the object thing has caused people to fixate on different aspects. But he came up with the term. Oh yeah, he also invented the graphical user interface. The whole idea of like Windows and stuff that you drag around and click and all those things. The whole GUI that you've lived with all your lives, but hasn't been around all my life. It got popularised in the 80s when the first Mac came out. So the graphical desktop, which Steve Jobs just ripped off from Alan Kay and his collaborators, he invented it. There you go. He also came up with the concept of the tablet computer. In 1971, he wrote a paper about a thing called the Dynabook, which was basically the iPad. The only problem was you just couldn't make it yet, because the hardware to have the screens be small and light enough and have enough memory wasn't there yet. But the thing about Kay is that he knew there would be, because of Moore's law. And he says, eventually Moore's law will shrink everything down, where you'll be able to put, a couple of megabytes of memory inside a little thing that'll look like a notepad, and you'll be able to create like a flat screen, and you'll be able to do all sorts of cool things with it. And yeah, Jobs, you say stole. It's like lots of people knew that idea, and of course someone had to actually turn it into a product and make it when the time was right, which is not trivial, but the ideas for it all came out of Kay and his collaborators. And most of this stuff was done in the early 70s, by the way. It's amazing how much of the kind of things that we might think of as kind of new in computer science were actually done very early on, and they just take decades before they filter down into the general world. So here is K. I would suggest kind of do a bit of research on him, read about him, watch some of his videos and stuff. There are plenty of them. Now, he's a bit of a strange old guy, and if you have to kind of get into his wavelength. He's so clever that he's unusual, and you might find that he seems a little bit like super abstract at times. And it's one of these things that I've got to appreciate him more over the years as I've got older and learned more stuff. Sometimes you feel as if he's a bit kind of in outer space at times, but he's a very interesting man. So I'm going to show you a little clip of him talking about some things.
Things that already exist. Now, I was just played a very minor part in the design of the ARPANET. I was one of 30 graduate students who went to systems design meetings to try and formulate design principles for the ARPANET, also about 30 years ago. And if you think about what the ARPANET, of course, became the Internet, and from the time it started running, which is around 1969 or so, to this day, it has expanded by about a factor of 100 million. So that's pretty good, 8 orders of magnitude. And there's, as far as anybody can tell, I talked to Larry Roberts about this the other day, there's not one physical atom in the Internet today that was in the original ARPANET. And there's not one line of code in the Internet today that was in the original ARPANET. Of course, if we'd had IBM mainframes in the original ARPANET, that wouldn't have been true. So this is a system that has expanded by 100 million, has changed every atom and every bit, and has never had to stop. That is the metaphor we absolutely must apply to what we think are smaller things. When we think programming is small, that's why your programs are so big.
So part of what he's getting at there is that the internet was designed in such a way that it was very, decoupled and everything, so that individual parts could fail and be replaced one at a time, but the system as a whole would hang together. And Kay wanted programs to be like that as well. Kay thought that object orientation was like that. It meant that your system would be a big collection of objects, and individual parts could be kind of swapped out and modified as time went on, but you wouldn't have downtime. You wouldn't have to switch the thing off to upgrade it. You would, it would kind of evolve or develop in a kind of incremental fashion. And he built systems that kind of worked that way, so that you could create big, complex systems that could survive over long periods of time and be relatively robust and not have to get switched off in the same way that the internet mostly doesn't get switched off, except when a couple of unfortunate key things like Amazon Web Services go down and break it all, which is not the way it was supposed to be. So that's part of what he's saying there. And here's another great talk by Kay if you've got time for it. Normal considered harmful. Okay, well, let's go back to what we're trying to talk about, which is objects. Turns out the question of what is an object is an old one, actually an ancient one. It's an old philosophical question. Anybody know about the ship of Theseus? Some of you do, that's good, right. So the ship of Theseus is the story told by Plutarch about Theseus, the founder of Greece. And the story is that Theseus and his mates went out on their boat and kind of conquered a whole bunch of parts of the Mediterranean or whatever, and eventually settled in Greece. And the idea is that the ship they supposedly used for the voyage was then kind of kept there as a memorial, of this great triumph. But as time went on and the years passed, people realised that the ship was it's a ship, right? It's a physical object, so bits of it would kind of fall off, or some of the planks would wear out and stuff. And it's well, what are we going to do with this really important historical monument? So we said, we'll patch it up, right? So when one of the planks would get too rotted, they would just replace it, and then another bit would fall off, and they'd put up, they'd fix it up and nail it back together. And this would kind of go on for years and years and decades until at some point somebody realised, we've probably replaced all of it by now. Like, every part of it has eventually worn out and had to be replaced. And all the time it was there, and it was a ship, and on any given day it was only changing a little bit. But eventually, there's probably not one plank of wood in this ship that was there originally. So in what sense is it the ship of Theseus? I mean, is it or isn't it? It has existed as an object, and it has a line of historical continuity. If we could point to say, there it is, there's the ship of Theseus, there are its coordinates. It's changing a little bit, but things are always changing. And then at some point it's like, yes, it's the ship of Theseus, but it's not made of any of the same matter anymore. And that's just a philosophical quandary as to, is it the ship of Theseus?
Isn't the other side then, if you take all the pieces, take out the ship, you restore them, and then
yes,
out of them, which is the written ship of Theseus?
That is the other part. The other part, exactly as I was going to say, is that the other thing is that if you take all the parts that got replaced and somebody took those and put them somewhere else and built a ship out of all the replaced parts, that must be the original ship of Theseus, right? So which is it? Are there two now? Do we have two identical objects? Or do we have two things that are not the ship of... anyway, so it's a philosophical conundrum to think about, but it kind of relates to this idea of, how objects they mutate over time, but they're in some sense still the same object. In our case, they've got the same address in memory, but their contents might change. And then you can have two things that have got different addresses in memory, but the same contents. And JavaScript will tell you they're not equal, but a human might look at them and say they are equal. So this whole question of what is identity is sometimes comes up. There are other variants of this. It's a classic conundrum. For example, is Doctor Who the same person after he regenerates, or indeed she? Now, by the way, one thing I did mention earlier is this thing about that human beings recycle all their atoms every so often. If you want to know the full story of that, it's a bit more complicated. The one you often hear is that your body recycles itself about every 7 years, but that's extrapolated based on some studies that were done of like parts of the gut and everything. Turns out different parts of your body replace at different rates, and some parts of your body don't get replaced. Some of the enamel in your teeth stays with you forever and can actually be used to radioactively date you. You can work out how old people are from their teeth, not by actually knowing how much radioactive carbon they've got in them. So the truth's a little bit more complicated, and actually there are claims that some parts of your neurons maybe don't change. So I'm just including that for completeness. But the principle of the thing, or at least the spirit of the thing, is nearly true, that things can recycle and somehow still be the same. Got one more version of this. This is an old British comedy programme called Only Fools and Horses, and a lot of British people know the ship of Theseus in this variant. It's not the ship of Theseus, we call it Trigger's broom. This is Trigger, and this is his broom. And he's had this broom for a long time.
This old broom has had 17 new heads and 14 new handles in its time.
How the hell can it be the same bloody broom?
Well, here's a picture of it. What more proof do you need?
We need a new brush.
No, nonsense. That's a marvellous old brush, that. I've had that for 14 years. That's only had 2 new heads and 3 new handles.
There you go. Okay. So while we're here, and I'm giving you this little bit of philosophy and history about where object orientation came from, when Kay came up with the idea of building programs out of objects, he was partly thinking of it as an analogy for biological systems, which are like this. They are adaptive and they recycle over time. So the whole point of objects was that an object is supposed to be like a biological cell, and that there's a whole bunch of machinery inside the cell, doing stuff, making it function correctly, but it's kind of protected from the outside world by a membrane that stops stuff from getting in and contaminating it. And that's basically why, what private variables are, right? The private variables of an object are the things that the object's in charge of, but other people are not allowed to mess around with them. You're only allowed to communicate by going through, by sending messages to the cell of a correct form. And this is what your methods are. You send a message to the object or the cell, and it processes it, and it decides what to do about its own internals, and then maybe spits something out at the end. And that's how the cell kind of maintains its integrity, unless something evil comes along, like a virus that fucks it up. But that was sort of the analogy. And Kay thought that the problem with programs in his day, like in the 60s, is that they were very brittle, very error-prone. One part of a program could muck about with another part of the program, and often did. And this would mean that this thing over here could break this thing. And he said, this is terrible. You need to put like shields around the parts so that you can get parts that like work on their own and they talk to each other. And if you do that, you'll be able to build much bigger systems that won't fall apart. They won't get super complex, and they'll have these kind of nice organic properties. Part of the reason that Kay could do this is probably that he did have a degree in molecular biology, so he knew about biology. He also has a degree in pure maths and electrical engineering and computer science. He's just one of these really clever people who just knows everything. And I think that can be useful. He had a lot of cross-domain expertise, which was good for generating new ideas. And one of those ideas was I mentioned it in a previous lecture, the Smalltalk 80 programming language, which is the kind of first or second object-oriented language, depending on how you think about it. And this is how it was all done. There was work done in the 70s to generate the early object-oriented systems. They also included the early, Windows icons, mice, and pointers, the WIMP user interface. It was called the WIMP, in part, the WIMP user interface because, it was so easy to use. It was for kind of weaklings, whereas hardcore programmers used the command line, of course. Now, I know that the command line is like retro cool nowadays, and obviously you can do a lot of powerful things on command lines, but the idea of making computers actually a bit more presentable and user-friendly was an idea that some people thought would be useful, and then he was one of them. So this Smalltalk thing that was actually developed in the 1970s, it invented the modern graphical user interface. It invented things like the model view controller pattern. That's where it came from. It invented the idea of WYSIWYG. What you see is what you get. How text editors... in fact, do you even know the term WYSIWYG? You maybe don't, because it's so normalized now, people don't even talk about it. In the early days of computers, you would have text editors where the thing you saw on the screen is not what you would get when you printed it, because it was full of control codes and basically full of formatting information. So the thing is, you would have to kind of type something out in your word processor and then print it to see what it looked like, and the printer added the formatting. But the idea was that it shouldn't be like that. What you see should be what you get. So if you want something to be bold or italic, it should look that way on the screen. And this is work that was done, and it was radical in its day. This was a new controversial idea. Other things they invented, integrated development environments, they were invented in the 70s in this system. Edit and continue for debugging, which a lot of people think is like a fancy new feature when it shows up in some systems nowadays. It's ancient, it was done in the 70s and then forgotten about. Virtual machines, again, portable machine images, basically Docker. Yeah, they did it all in the 70s. And this was all done by the XEROX Corporation. The photocopier people who they had a lab, because Xerox felt that because they'd made photocopiers and paper for offices, they felt that we're the company that provides office materials. And in the 70s there was a lot of talk about one day there will be paperless offices. We'll all use electronics and we won't need paper anymore. And I guess somebody at Xerox realised, well, if that happens, that'll be bad for us because our business is selling paper. So if the office goes paperless, we want to be in there. So they had a research lab trying to figure out what the paperless office might be, hoping that they could then, sell you computers and things instead. But they messed it up. So Xerox, in fact, did a lot of the pioneering work and basically could have been Apple if they hadn't made a mess of it. So this is a funny old video that during the 70s they did all this research work, created all these brilliant ahead-of-their-time systems. By the end of it, they had kind of fallen out of favour, corporate politics and stuff. But towards the end, they sort of tried to commercialise some of this work. And this is an old advert trying to show people what the future of computers, the paperless office and stuff would be. This is probably late 70s, early 80s, probably early 80s. And you've got to understand, this is a time when most people would not have seen a computer yet. You didn't have home computers, people hadn't seen them. Computers were big things in banks and universities, and they didn't have screens. All the modern stuff that we're used to just hadn't happened yet. Yeah.
Good morning.
Good morning.
You come into your office, grab a cup of coffee.
Morning, Fred.
And a Xerox machine presents your morning mail on a screen.
What's the mail this morning? This one looks interesting. Let's take a look at this. I'm going to need a couple of copies of this.
Push a button, and the words and images you see on the screen appear on paper.
Oh, thank you. Thank you, Fred. Fred, I think everybody on the routing list should see this.
Push another button, and the information is sent electronically to similar units around the corner or around the world. This is an experimental office system. It's in use now at the Xerox Research Center in Palo Alto, California. Soon, Xerox systems like this will help you manage your most precious resource, information.
Anything else? Flowers. Well, what flowers? My anniversary. I forgot.
That was another one of the big things in the late 70s into the 80s. They started thinking that the thing we're going to need next for computers is digital assistants. So not only would you be able to use the computer and click on stuff and do things, there'd be something inside there that was intelligent and would be able to kind of help you organise your life a little bit, anticipate some of your questions, tell you when your anniversary is. And of course, they never managed to build that back then, but they always felt that was like the next step. And indeed, the modern digital assistants, your Siris and whatnot, are basically all in that spirit of having these agents that can, automate certain nuts and bolts aspects of your life. It all kind of came out of that vision from the 1970s. Unfortunately, Xerox built all this stuff, and it was like decades ahead of its time and brilliant, but there were problems. Realistically, it would have been too expensive to market at the time, but also apparently Xerox kind of got cold feet and sort of realised that if all this stuff took off, if people had all these computers and stuff, you wouldn't, if you had electronic mail, which was a novelty, then you'd be sending emails and you wouldn't be photocopying stuff, and it would be very harmful to their photocopier business. So they basically pulled out, and that was one of these classic things of you're right, but you're also terribly, terribly wrong. It's true that if this stuff comes along, we won't use photocopiers anymore, but it's going to happen. And what you should do is you should get in there, because otherwise it's going to come along and eat your lunch. But they screwed up. They were too concerned about protecting the old business that they didn't allow the new one to flourish. And that's partly what Steve Jobs himself thinks about that history. So this is an old clip from the 90s. I actually watched this program when it first came out. And this is Steve Jobs talking about how he did a deal with Xerox. He said, I'll give you $1 million of Apple stock back in the old days when Apple was a tiny little company, if you show me your research lab and you get somebody to take me around, because I've heard that you're doing lots of cool stuff. And he did, and he got given the tour, and he saw the graphical user interface, object orientation. He's going to talk about it himself. He saw all these things and basically stole them or imitated them, went back to Apple and told his guys, do that. And that's where Apple came from.
It all began in 1971 in Palo Alto, just south of San Francisco, when
So I will jump ahead to the part I've indicated where Steve talks about this experience.
Steve Jobs had co-founded Apple Computer in 1976.
And there's Wozniak, who was the actual clever one, the one who could program. Steve Jobs can't write a fucking line of code to save himself.
The first popular personal computer, the Apple II, was a hit and made Steve Jobs one of the biggest names in a brand new industry. At the height of Apple's early success, in December 1979, Jobs, then all of 24, had a privileged invitation to visit Xerox PARC.
And they showed me really three things. But I was so blinded by the first one that I didn't even really see the other two. One of the things they showed me was object-oriented programming. They showed me that, but I didn't even see that. The other one they showed me was really a networked computer system. They had over 100 Alto computers, all networked, using email, et cetera, et cetera. I didn't even see that. I was so blinded by the first thing they showed me, which was the graphical user interface. I thought it was the best thing I'd ever seen in my life. Now, remember, it was very flawed. What we saw was incomplete. They'd done a bunch of things wrong, but we didn't know that at the time. It's still, though, they had the germ of the idea was there, and they'd done it very well. And within, 10 minutes, it was obvious to me that all computers would work like this someday.
It was a turning point. Jobs decided this was the way forward for Apple.
He came back and, I almost said asked, but the truth is demanded that his entire programming team get a demo of the Smalltalk system. And the then head of the science...
This woman, Adele Goldberg, is another of the kind of unsung heroes of computing. She developed a lot of the Smalltalk system and wrote the book about it that explained how it worked. She's a very interesting person.
Center asked me to give the demo because Steve specifically asked for me to give the demo. And I said, no way. I had a big argument with the XEROX executives telling them that they were about to give away the kitchen sink. And I said I would only do it if I were ordered to do it, because then, of course, would be their responsibility. And that's what they did.
The mouse is a pointing device that moves a cursor around the display screen.
Adele
so this is the actual system being used, where the voiceover has to explain to you what a mouse is, because people didn't know yet. And this thing over here, this is an IDE. This is code in here. This is the programming in here. And it's organized into classes and packages and stuff. And you can actually go in and edit the code live in the system, and it just instantly reloads. There's no linking or anything like that, because it's all dynamic. Kind of amazing stuff.
Her colleagues showed the Apple programmers an Alto machine running a graphical user interface.
A selected window displays above other windows, much like placing a piece of paper on top of a stack on a desk.
The visitors from Apple saw a computer that was designed to be easy to use, a machine that anybody could operate and find friendly, even the French.
Choose one.
I think mostly what we got in that hour and a half was inspiration. And basically just sort of a bolstering of our convictions that a more graphical way to do things would make this business computer more accessible.
After an hour looking at demos, they understood our technology and what it meant more than any Xerox executive understood it after years of showing it to them.
Basically, they were copier.
By the way, that guy there that you just saw, the previous one, he's called Larry Tesler. And his amazing claim to fame, well, he's got a couple, but one is he invented copy and paste. Now, I remember hearing that story a long time ago and thinking, that's ridiculous. Copy and paste is not an invention. It's a very obvious idea. Anyone would have come up with it. But actually, for a long time, people didn't come up with it, that if you wanted to move things from one program to another, remember, you couldn't run multiple programs at the same time because you didn't have Windows. So you were running like one program, and you'd have to save out the stuff in that program into a file, and then load another program separately and load it back in and hope that those programs could both read the same file format, which they often couldn't. And that's how you would have to move data between programs. And Tesla came up with the idea that, no, you should really take the program in the first window and point at the stuff you want and say, copy that, and go to the other one and say, and put it there. And he came up with that idea, and I presume actually implemented it. You know, these guys didn't just dream about stuff, they built it as well. So yeah, he invented copy and paste. Imagine if he got royalties every time someone copied him, but he doesn't. But
that just had no clue about a computer or what it could do. And so they just grabbed defeat from the greatest victory in the computer industry. Xerox could have owned the entire computer industry today. Could have been, a company 10 times its size. Could have been IBM. Could have been the IBM of the 90s. Could have been the Microsoft of the 90s.
So there you go. And he stole it all from Alan Kay. Right, games. So a bit of a detour there, but we were just trying to talk about, what objects are, why we use them in games, where the idea of object orientation came from, what it means, and so on. So let's say we're trying to make Pac-Man. What are the relevant entities that you would carve your Pac-Man universe into? Just shout out suggestions for Pac-Man himself as an entity. The ghosts are an entity, or entities, yes. The things he eats, the little pills. Yeah, see, the walls. The walls is an interesting one. Is each section of wall an entity, or is the whole maze an entity?
That sounds insoluble philosophical.
Yeah, you just make a decision. You can do it either way. You might want to think of each wall piece as its own little independent fragment, or you might somehow treat the whole set of them as a single environment object that you do something with. And my point here is that often there's not a formula for doing it. It's kind of a matter of discretion. But you have to decide how to. There's an old phrase about carving nature at the joints. When you're kind of analysing a system, you've got to decide where you want to place the boundaries on a thing. And part of it's taste, and it's a thing that you kind of get experience with over time. But you've got the right idea. If you were making Pac-Man, you'd say, right, we need a Pac-Man, and he's got his position and his velocity, and he's got behaviours like being able to eat stuff and collide with stuff, and and so do all the other things. So you got the pills and the maze, the ghosts. So as I've said, each of these entities is going to have a position and a kind of visual representation usually, and a set of rules. And the idea of how you build systems like this is you identify the entities that you've got, and you work out what behaviours they need to have and what state they need to encapsulate, and you just go and write each individual part, and then you kind of start getting them to talk to each other, and that's how the system kind of comes alive. And those sort of things. So this is why you get interesting things like, you have the ghost entities, and they've got code for how they behave over time, but one of the things the ghosts need to do is they chase Pac-Man, usually, unless Pac-Man's powered up, in which case they run away. So they need to have a way of talking to Pac-Man to say, are you in scary mode or not? So I can work out whether I'm supposed to be following you or running away from you. And that's what you would do. The ghost code would have a message it could send to the Pac-Man object to say, are you in the powered up state or not? And if he's not powered up, the ghost would then say, okay, I'm going to try and route find towards you. And if it's not, they would route find away. And everybody's kind of taking care of their own business. The ghost is taking care of their business. Pac-Man's taking care of his business. He has to do things like, he has to tell the ghosts what state he's in, because the game logic requires that, even though, Pac-Man doesn't want to be eaten, but the system under the hood is having to send all these messages around to coordinate the emergent behaviour of the system. So as I've already mentioned, when you're making a game, you're kind of making a flick book that you're drawing as it's being played. Now, previously I spoke about the visual aspect of it. You draw a picture and then you do the swaps during the V-blank. But the other thing is, well, how do you draw the picture though? How do you compute the nature of the scene before you draw it? That's to do with working out, the physics of the world, working out, the car was here on the previous frame, where's it going to be on the next frame? And you have to compute all that with some kind of, physics system or game logic. So you move each individual object, you move all the pieces in the board to their new positions, and then once you've done that, you render them, and then you switch the pictures. It's kind of obvious, but that's what you have to do. So that's basically how it works. That when you have your simulation, you know the state of the simulation at time t, and then you do some stuff and you draw a picture, and then you get to a new frame and you say, okay, what time is it now? And it'll be like t plus 1 or t plus 1.5 or how many units of time have passed. And then you go to all the objects and you say, okay, could you now update yourself by that amount of time? Take 1.5 units of time and move yourself forward, and you move and you move and you move, and then work out who's colliding with each other and resolve everything to some final state. And then once you've got that state, now everybody renders themselves in their new position. And then once you've done that, you do the buffer switch and you get the new frame. And that's what's going on. So it's a lot like making stop motion animation, if you think about it. And here's a little clip from another British comedy show. Do you know the Wallace and Gromit cartoons? The little plasticine dog guy? Right, well, this is about that. I don't know if you've ever seen an interview with the real animator, Nick PARC. He's a lovely guy, but he can be a little bit, well, you'll see what he's like, because this is a comic interpretation of what it's like to talk to him.
It's fascinating how you do it. It really is.
Well, it's very time consuming. On a good day, we'd get about a second of finished film.
Is that just a second? Is that...
Well, less if it was a particularly tricky bit, an action sequence or something. Let me show you. Say he wanted to do a wave. a sort of dismissive gesture like that. What you do is, first of all, you move his hand just a tiny amount,
Right.
and then you'd move one finger, again, a tiny amount.
Right.
Second finger, just a tiny amount. The third finger, just a tiny amount. And then we'd have to move the eyes around. Again, just a tiny amount. And the other one, a tiny amount.
Now, bear in mind, you do have to do this if you've got like a character animation system. You have to move all the bones in the skeleton for each animation pose from one position to the next. So this is, luckily you get a computer to do it. You don't have to do it manually, but it's
Then it's
same idea.
click, click, 2 frames. And then I suppose his feet should waggle, his toes. So the first toe, we'd move it down just a tiny amount. And the second toe would come up a tiny amount. The third toe down, just a tiny amount. Then we move up to the hand again, move out a tiny amount, and this finger, just a tiny amount, and the next finger, just a tiny amount, that finger, just a tiny amount, then we come up again to the eyes to bring them round some more, tiny amount, this finger, a tiny amount, this finger, and then the eyes would come round.
It's almost as boring as listening to these lectures, isn't it? Speaking of which, anyone fancy a pint? We'll leave it there and we'll pick up the rest of this on Wednesday.